We can find out the factor of safety using the stress envelope in the case of MSST, that is the maximum shear stress theory and the maximum principal stress theory. So we'll consider here maximum shear stress theory, and we are given the load condition that we have principal stress sigma A is equal to 125, sigma B is equal to 175, and we have SYT is equal to 250 megapascal. So in the quadrant 1, you have to show the rectangle passing through SYT and SYT. So these two straight line here is the envelope in the case of maximum shear stress theory. Then you have to join the SYT and SYT in the quadrant 4 and quadrant 2. So this one is representing the face in the case of maximum shear stress theory. Again we have a rectangle. So this face here representing the maximum shear stress theory. And we are given here the principal stress sigma A is equal to 125, sigma B is equal to 175, SYT will get equal to 250 megapascal. Using this load diagram, we have to find out the value of factor of safety. So we'll select here this 1 cm and this one is 2 cm. This 25, 50, 75, 100, 125, 150, 175, 200, 225 and 250. So we have here approximately will say here we have 2 unit is equal to 25 megapascal. So these are the 2 units. So we want to locate here 125. So this one is 25, 50, 100 and this one is 125. So this point here will corresponds to sigma A is equal to 125 megapascal. It's a tensile in nature. Sigma B is equal to 175. So we have 25, then we have 50, then we have 75, 100, 125, 150 and 175. So this point represent here the sigma B value, which is equal to 175. So using the value of sigma A and sigma B, we can locate the point A on the graph. So to locate the given state of a stress here, we have to draw the vertical through sigma A, which is 125, sigma B is equal to 170. So this one is the point A, which is representing sigma A equal to 125 and sigma B is equal to 175. So this line here is called as load line. This line, if extended, will meet the boundary at this point. That point will be equal to B point. So you have to record the point A and then you have to record the point B by joining OA, and you have to extend OA till will intersect to the envelope. If the position of point A is here, then the extension of OA will meet on the right boundary. Right now it is meeting on the top boundary. Now you have to measure the distance OA and measure the distance OB. So we have to measure the distance OA here. So we'll keep the ruler along the OA and we'll measure the distance between O to A. So this is approximately equal to 6 cm. So we have OA is equal to 6 cm. And we can measure distance OB. So OB is 8 plus 8.5 and 8.55. So we have OB is equal to 8.55 cm. So in this case, we have factor of safety will be the OB divided by OA. That is, we have 8.55 divided by 6. So approximately we will get a factor of safety equal to 1.425. And in this case, the maximum principal stress is sigma B. So numerically also you can find out the factor of safety, which is equal to SYT divided by maximum value out of sigma A and sigma B. So this time it's a sigma B. And we'll get this value of SYT is equal to 250 divided by sigma B is equal to 175. So this one is the exact answer, and graphically also we get the answer equal to 1.425. So we are getting this answer is 1.428. Almost same answer you will get. So procedure is that whatever the state you are given here, sigma A and sigma B, we can locate here on any point. Then join the point O with A, measure the length of OA, then measure the length equal to OB. Factor of safety is defined as OB divided by OA. Otherwise, the factor of safety numerically is defined as SYT divided by the maximum value. So this one is maximum value of either sigma A or either sigma B. Both these answers are very closely matched. So graphically you can find factor of safety if we are knowing the stress envelope in the case of maximum shear stress theory. One additional concept we want to develop in the case of maximum shear stress theory, that is the torsional shear strength, and we want to show here the value of the pure shear on this graph. In the case of the pure shear, there is no normal stress is acting on the machine part, only the shear stress will act. So if we have a state of a stress is purely consist of the shear acting, that is the value of tau xy and the value of tau xy, sigma x will be equal to 0 and the sigma y will be equal to 0. This state of a stress is called as pure shear. Pure shear you will get when we have a shaft and the shaft is subjected to twisting moment equal to torque. So suppose this shaft is subjected to twisting moment is equal to T, then everywhere we have a case of pure shear. So this one is representing the x phase, and on the x phase the coordinate is given as sigma x and tau xy. Out of that we have sigma x value will be equal to 0. On the x phase, this shear stress above the origin will rotate in a anti-clockwise, so that is taken as negative value is minus tau xy. And if you consider here the y phase, so this one is y phase. For this y phase, sigma y will be equal to 0. So y phase has a coordinate of sigma y comma tau xy. So y phase has sigma y contribution will be 0. We are on the y phase and this shear stress above the center will rotate in a clockwise, so will taken as positive value. Using these two coordinate x and y phase coordinate, we can draw here the Mohr circle and we can represent here the pure shear condition. So this axis is representing the normal stress, this one is representing the tau or the rotation is clockwise. This axis represent again the shear, but rotation is anti-clockwise, that is negative, and this one is negative value of sigma. X coordinate will be 0 and the y coordinate will be equal to minus tau xy. Minus tau xy we can locate here. That value will be minus tau xy, and the y phase we can locate at the same distance from origin at a distance equal to tau xy. So this point is same as equal to tau xy. So this one is our x phase and this one is our y phase. Naturally we have center at origin and we'll draw here full circle. That will represent a Mohr circle. So this one is a Mohr circle and it has a radius equal to tau xy. So this one is the largest principal stress equal to sigma A, and this value is same as equal to tau xy. This one is the minimum value of the principal stress, that will be equal to sigma B, which is equal to minus tau xy. In case of pure shear, we have sigma A and the sigma B are identical value but negative value. So in case of pure shear, that is the shaft is subjected to torsion, then only the shear stress is produced, that is called as pure shear. On this state of a stress here, sigma x and sigma y is 0, but if you rotate it by 90 degree, you will get the principal stress. So same state of a stress if rotated by 90, it means that this angle will be same as equal to 2 times of theta p, so you have to rotate it by 45 degree. In the Mohr circle, the angles are 2 theta, so this value is same as equal to sigma A, which one is tension, and sigma B is in compression. And this angle is same angle equal to 45. So for pure shear we can say we have value of sigma A is equal to minus sigma B. Both value are equal in magnitude. So for pure shear we have sigma A is same as equal to negative value of sigma B. So this one is again a straight line having slope equal to minus 1, that is equal to angle is 45. Since here the slope is equal to -1, so we'll draw here one line which is inclined at 45 degree. So it will bisect the quadrant 2 and quadrant 4. This line represents here a special load line because for this line we have sigma A is equal to negative value of sigma B, or we have the case of pure shear. So this one is also representing the case of pure shear. And this line makes an angle of 45 degree and is perpendicular to this fence as well as perpendicular to this fence. The equation of this line is sigma A is equal to minus of sigma B. This line is called as the pure shear load line. So if you take any point on this line, the value of sigma A and the absolute value of sigma B are 1 and same. Everywhere this is true. That is the magnitude of sigma A and the magnitude of sigma B, they are identical value. Here this line is also a straight line having slope equal to 1 but positive slope. So we have y is equal to mx plus c, and we have y-intercept is minus syt. On y-axis we are plotting here sigma b. For this line we have slope is equal to 1. So we have 1 multiplied by x is sigma a, and we have y-intercept c will be y-intercept is equal to minus syt. So this line has the equation of mx, that is 1 into sigma a, and plus c means minus syt. So this line and these two lines, so line number 1, which one is representing the pure shear load line, and line number 2 represents the boundary condition. So we can find out this value here, the intersection with the boundary, and that value is called as the torsional shear strength in the case of MSST. So this value represent here the value of torsional shear strength, that is the shear strength in the yield. Equation for line 1 is sigma A is equal to negative of sigma B, and the fence has equation 2, that equal to sigma B is equal to sigma A minus syt. And remember here we have sigma A and sigma B. That value already known to us is a tau xy, that is same as equal to ssy at the yield point. So the maximum possible value in this case will be sigma A, and this value of sigma A will be same as equal to syt divided by 2. So this one is same as syt divided by 2. Even this value is also equal to syt divided by 2. All these values are syt divided by 2. So in this case we have sigma B will be as it is. This value of sigma A we can write as negative of sigma B is minus syt. So we can have either this equation or either this equation. This value is also equal to ssy, that is the torsional shear strength. So we can write here plus minus syt, both intercept, either this intercept or either this intercept. These two value will be equal to sigma B is equal to plus minus syt. So plus minus syt is meaningless here. Since here the value of sigma B it says represent the shear strength in the yield. So we have since here sigma B is equal to ssy. So from this equation we have ssy equal to syt divided by 2. This equation is obtained for MSST, maximum shear stress theory. So remember here the torsional shear strength in the case of MSST can be obtained by drawing a line in which we have pure shear, and if we have pure shear then the sigma x is 0, sigma y is 0. Then we can find out the principal stress sigma A, sigma B. We get the Mohr circle, and according to the Mohr circle we have sigma A is equal to minus sigma B is equal to tau xy. At yielding this value is same as equal to ssy. So this point of intersection is obtained by two lines here. One is a dotted line which is representing the pure shear load line, and for this line we have sigma A is same as equal to minus sigma B. This fence or either this fence, both fence has the equation equal to y is equal to mx plus c. Slope is positive and intercept here is minus syt, and here we have intercept is plus syt. So we have sigma B equal to sigma A minus syt. Solve the two equations simultaneously. Solve for sigma B or sigma A. Both value represent here the torsional shear strength. So we have torsional shear strength is always equal to syt divided by 2. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.